we will see what are recursive languages. In our previous class we were talking of whether this is decidable or this is not decidable. So we will see what is the difference between these two, whether my recursive language can come to a conclusion that whether this problem is decidable or not. We will see that. Fine. So here we will see two class of languages. One class is what? One class which corresponds to what we commonly think of as algorithm. What an algorithm does? Okay, we are having a problem, we come up with a problem, we just want to solve that problem using certain finite number of steps, and at the end of the day there is an output. It must have an output, right? So this is one class of language. In other words, if we have to express this one, we will we can say it like this: my Turing machine will halt, and whether it is reaching an accepted state or not. That means we will get to know an output, that okay, for this string whether it has reached my accepting state or whether it has not reached my accepting state. Fine. So it will halt. But there is one second class of recursively enumerable languages where my Turing machine will never guarantee whether it will halt or not. There may be some situation where for a particular input it is not going to accepting state, fine, but it will never halt. It will keep on processing the input string. So these problems will be undecidable, means we cannot come to any conclusion that okay, this string will be accepted or not, because it has not halt, it is still going on. Okay, so there is an example of this kind of language where if you follow the ebook which I have shared with you, there you can see a coded pair example is there called diagonalizing. Okay, binary string diagonalizing. There you can see that it is never halting. Okay, it is not, it is keep on processing it. So this are the two classes of languages. Now if we have to define what are recursive languages, we will define it like this. See, we are having a language L. It is recursive if that language is getting language for some Turing machine M. Okay, so it is a language for some Turing machine M. So when it will be a language for the Turing machine, if these two situation holds, what are those? If W is in L, then M accepts, right? So obviously if W is the type of the language which my Turing machine is going to accept, then we will call okay, this string is going to get accepted by my Turing machine, and therefore since it is moving to the accepted state, so it is halting. But if W is not in L, M eventually halts, although it never enters an accepting state. So you can see here this is the type of the first class of first type of languages. What was the first type of language? Here you can say, you can come up with an output, okay, whether my string has got accepted or my string has not got accepted, right? It is having one output. In the first case it is being accepted, in the second case it is not being accepted, right? So it's a special class where all the decidable problems will be there. Okay. Now, a Turing machine of this type corresponds to our informal notion of an algorithm. What I told you, that these recursive languages or this class of languages are those languages which are decidable. So it will always come up with an answer of yes or no, right? And here in case of in place of rather language, we will say problem. For this problem, whether it is decidable or not. Okay, fine. Now, as mentioned above, the Turing machines that are not guaranteed to halt may not give us enough information ever to conclude that string is not in the language, right? So since the Turing machine has not finished its job yet, so how can we come to the conclusion that okay, my string has got accepted and has not got accepted, and we are not quite sure that when the processing will stop? So these are the undecidable problems, okay, where we cannot come up with any kind of decision. Now, so what we are doing? We are dividing the problem solved languages between two, that is decidable. Those can be solved by an algorithm, and another class is undecidable, which cannot be solved by an algorithm. Okay. Now, the recursively enumerable language are the total class, means it may consist of the decidable problems as well as undecidable problems. Let us see a pictorial representation, it will be clearer to you. You can see here, just see here, two circles are there. Outer circles are what? RE, that is recursively enumerable. So it is consisting of both kind of languages, right? And recursive language are part of it or a subset of it, where we will just work up with the decidable problems. Okay. Now you can see here we have positioned the non-RE. There are even languages which are non-recursively enumerable languages, and also we have shown that LU or universal language, we shall prove shortly to be recursive, although it is RE. So here in the next lecture you will see LU. LU means what? The language which gets accepted universally, means we will come up with the concept of universal Turing machine. There you can see the LU means what? All those languages which a Turing machine can accept. Okay, that will come under the class of LU, and recursive languages are a part of it. Okay, so there has to be some special feature for a language to be recursive. Fine. Now, how complements work here in this class of languages? Now we have to see what are the complements of recursive and RE languages. Okay. Now we will show that our recursive languages, means the smaller part, which is a part of RE also, are closed under complementation. So what it will be like, what? For if L is recursive, then L dash will also be recursive. Okay, we will just prove this property for two different class of languages. So here theorem 1 says, if L is a recursive language, then its complement is also a recursive language. Just see the diagram. Why we have just swapped between accept and reject, means since we are constructing one L dash, right, one complement language, so here if one language accepts this one, it is going to get rejected by its complement, and the vice versa, right? So here what we will assume, first we will assume a language, say L, it's a language for the machine M, for some Turing machine say M, and that always halts. That always halts. Why? Because it's a recursive language, it is going to halt always. We know the property already, right? Now here we have constructed on Turing machine M dash such that the language will be obviously L dashed, and it is the language accepted by the machine M dashed, right? Here just see the diagram, we have depicted it. Now what will happen, how we are going to modify M so that we can create the M dashed. How we are going to modify M? The accepting states of M are made non-accepting states of M dashed with no transitions. It is same as like, say, whenever we had one DFA, whenever we had a finite automata, we had to construct a complement of that machine. How we started? We made all the non-final states to final state and the final states to non-final state, right? So here the same thing is we are going to do. Whatever the accepting states of M are, we will just convert to non-accepting states in case of M dashed, and it will have no transitions. That is, in this state M dashed will halt without accepting, right? At the accepting state in case of Turing machine, we have not seen any transitions there. So here whenever we are converting my non-accepting state to the accepting state, we have to remove the transitions as well. Okay, now M dashed has a new accepting state R, where there are no transitions from R, right? So here we have to incorporate one new accepting state as R. Now for each combination of a non-accepting state of M and a tape symbol of M such that M has no transition, that is M halts without accepting, add a transition to the accepting state R. How it will be converted? Say, in case of M, means which my original machine is, there were few non-accepting states, right? But we have converted those non-accepting state to the accepting state in case of M dash. Now we have discarded all the transitions there. Now what is the go now? Okay, now we have to pick up each originally non-accepting state and the tape symbol which it was processing, and say there has no transitions in original machine, right? So what we will do here, since there were no transitions, here we will add one transition and it will directly move to the accepted state R, right? Why we are doing like this? Because see, in the original machine there were no transitions for those non-accepting states, so it is not means it is not contributing actually. So whatever we will do here, since we have converted those to the my accepting state, so that will go to the totally accepting state obviously, okay, since we have converted it to the accepting states. Now since what we have got here, since M is guaranteed to halt, in originally my M was a recursive language, so it can guarantee the halting. So here, since we have converted all the non-accepting states to the accepting, and we have made the accepting states to the non-accepting, and we have mapped the transitions correctly, that means my M dash will also halt. That means what? If my M can accept L, my M dash will accept L complement as well. So it is closed under complementation. Fine. Why? Because both L and L dash will be ultimately recursive language only. Right. Now let us see, is it true for my recursively enumerable or not? What the theorem is saying, if both a language L and its complement are recursively enumerable, then L is recursive, right? So here we have already seen that that a language and its complement are closed under recursive. We have seen it, and here we have to see, we have to, if we can prove that if both a language L and its complement, both of them are recursively enumerable, then if we can prove that a language and its complement both are recursively enumerable, then that language is what? Obviously recursive, because that property holds for recursive languages only, right? So how to prove it? Here we are just taking off two different machines, namely M1 and M2. First one is the original machine and second one is the complement. The first one is accepting the language L and the second machine is accepting the language L dash, right? So we will just simulate it parallelly. We'll make the Turing machine works parallelly. Now how we are going to simulate it? If we incorporate a two-tape Turing machine, the thing will be done, because we are just running one language L and another language L complement, so that can be done by two-tape Turing machine only. And obviously we will be able to convert the two-tape Turing machine into one-tape Turing machine. We can do it. So one tape of M simulates the tape of M1, means whenever we are going to convert it to one tape, or in how the multi-tape is going to work. So one tape of TM will do what? It will simulate the tape of M1 and other tape of M will simulate the tape of M2. So means how we are going to convert it to this multi-tape to single one-tape Turing machine. If you remember, for k-tape multi-tape Turing machine, what we did, we used we just whenever we tried to convert it to one-tape Turing machine, we just use k different slots, right? So the first slot was dedicated for I'm not talking of the finite control, just about the input symbols of the tape. The first track was dedicated for first tape of the multi-tape Turing machines. Next track was dedicated for the second tape, and this fashion. So here we will again, the first track will be for M1 and the second track will be for M2. Okay, now if input W to M is in L, we know that what my whenever it can process it, since it is accepting that means that if we consider the fact that my W is in L, that means my W is a language being accepted, right? Then what it will do, it will get accepted by the machine, right? Since W is a class from the language L, so M1 is definitely going to accept it, and it will, if M1 accept it, then it will do what? It will halt, my machine will halt. And if W is not in L, then it is in L dashed, right? So either of the two will exist. W may be in L, may not be in L. So if it is in L, it will get accepted by M1, and if it is not in L, it will get accepted by M2, right? So whenever my M2 accepts, M halts without accepting, right? So either of the situation, whatever may be the situation is, whether W belongs to L or it may not belongs to L, in all the chances it will halt. In one case it will accept the string and halt, in the other case it will ignore the string and halt, but ultimately it will halt. Since M is always halting, we can say that it is in recursive language, right? Since for both the cases it is halting, we can come up with an output. That means L is a recursive language. So it is the two theorems are very important and it has been proved. And this much for now, and in the next class we will see this one, that is universal language and universal Turing machine. Okay, thank you.